So today we're going to continue talking about various examples of distributions. And so for the next lecture or so, we're going to kind of start building up our pantheon of different distributions that we should know. And these will show up on the final exam. And they're generally just kind of the basic distributions that one should know coming out of a probability course. And we're going to start simple. And we're going to begin talking about the discrete uniform distribution. So discrete uniform distribution. And this is one of the simplest distributions. It's a distribution where we have values distributed discretely over some interval. So let's say a random variable x distributed as, we're going to say UNIF, uniform, and we're going to say it's distributed on the numbers 1 to, let's use some lowercase n here. And so this is going to be a notation for discrete uniform distribution. And we write x distributed uniform 1 to n to mean that x can take on with positive probability any of the values 1 to n, and it does so with equal probability at all these values. So I can draw a picture, say, of, this is by PMF for the discrete uniform distribution. The support is 1, 2, 3, all the way up to n. And if each of these n values take on or have equal likelihood or equal probability, uniform probability of occurring, then the mass at each of these should be 1 over n. So our PMF looks like this. So typically when we name a distribution, we're really kind of thinking, the most natural way to think about it is what is the PMF or the PDF for the distribution. So this thing means that kind of PDF. And once we have the PDF, we can look at all the other things we've looked at so far. We have the PDF, we can look at the CDF, we can look at the expected value, variance, moment generating function. And so that's what we're going to do for these distributions. So we're going to start with a discrete uniform. That's the PMF. And we can write this in symbols, i.e. little f of x is equal to 1 over n when x is equal to 1 to n and 0 otherwise. And given the PMF, we can, of course, derive the CDF. So let's look at the CDF of this then. The CDF we know is a cumulative distribution function. And it is, we have our nice little formula that says the CDF, capital F of x, is the sum, where I goes from the lowest value in the support all the way up to whatever value little x we're looking at, and we just sum f of I for all these values. If we do that for the discrete uniform, it's a pretty simple case. If I is 1, then we're just going to sum up this first thing, so we will get 1 over n. If I is, so this is I, if it is greater than or equal to 1, but less than 2. So we're going to sum. I suppose if I, the base case here is if I is less than 1, then we're summing all the mass less than 1, which is 0. As soon as it hits 1, it jumps up to 1 over n, so we add that to our sum. Then we continue marching on, march, up to 2. Once I hits 2, so if I is between 2 but less than 3, we're going to include the second piece of mass. We go to 2 over n, and you can imagine, similarly, when we get up to 3, that's between 3 and 4, including 3, excluding 4, we get 3 over n, and we march up all the way up to, eventually we will get n over n, or 1, if I is greater than or equal to n. And so writing out the formula is maybe not the best way of thinking about the CDF. We can actually draw a graph of the CDF. So here's capital F of x, here's x. Again, our support is 1, 2, 3, all the way up to n. And our CDF, it's drawn red here, it's 0 up until it gets to 1. And then it jumps up to 1 over n. That continues till it gets to 2. At 2, it jumps to 2 over n. That goes to 3. At 3, it jumps to 3 over n, and so forth. We'll kind of leave out the details. At some point, and we know it has to hit 1. And so what's going to happen is at n, it's going to finally jump up to 1. And bigger than n, the CDF is just going to be 1, because we've summed up all the mass. And the CDF conforms to our definition of a CDF. So the properties is this thing is 1, what are our properties? Is that it's non-decreasing, 2, it's right continuous. And we can see that because if we come from the right-hand side here, say this way, the limit of the function is equal to the value of the function. And I guess the third property, these are a little bit out of order, is that the limit at negative infinity of f of x is 0, right? If we go out far enough to the left there, it's 0, and the limit as x goes to infinity of f of x is 1. So it satisfies the properties that we require for CDF, and it's the CDF for the discrete uniform. And it's just a little step function, and we know it has to kind of be a step function because this is a discrete random variable. And so that's the CDF. Okay, so what else can we investigate? We could look at expected value. So expected value for the discrete uniform. And our definition for, so E of x, if x has discrete uniform on 1 to n, E of x is, we know our definition is the sum, and we can sum just over the support, so that goes 1 to n, of x times, or I should say I in this case, because our index is I, times f of I. Or equivalently, we could write this in terms of x. It doesn't really matter. And when we do that, of course, if we just plug in for what f of I is, it's 1 over n in all cases. We can bring that out. So we get 1 over n times the sum. I goes 1 to n. And you need to know a little trick, a little formula, thanks to Gauss here, that the sum whoops, we forgot our I here, so there's 1 over n times the sum, I goes 1 to n of I, and that sum is, by handy little formula, is n, whoops, little n by n plus 1 over 2. Our n's cancel, and we're just left with n plus 1 over 2. And so this step here, where we get this n by n plus 1 over 2, that's just because we know a formula for simplifying the sum of the numbers 1 to n. And you can Google around and find cute little proofs of that. Not too bad. So expected value is n plus 1 over 2. And that kind of makes some sense if you were to go back to our distribution and you were to look at kind of, okay, where would I put my fulcrum to balance the mass here? I would put it, basically, my fulcrum point here would be at n plus 1 over 2. And that would kind of be the middle point to balance the mass on a bar, as it were. And that's one way we can interpret expected value. Okay, so we got expected value. Why don't we look at the expected value of x squared? Expected value of x squared. And again, our formula, so we can change from I to x. The dummy variable doesn't matter. We say it's the sum over our support, and now instead of I, or instead of x, we have x squared. This is the law of the unconscious statistician, and then of course we have to multiply by the PDF, or the PMF in this case, which is f of x. And, oops, let's make sure our index is x in this case. X squared, and the PMF at each point in our support, again, is just 1 over n. So that's not going to matter too much. Comes out as a factor, and it's 1 over n times the sum. I goes 1 to n of x. And in this case, or x squared. In this case, there's another formula we can look up. I definitely don't expect you to memorize this, but the sum of the squares of the first n squares has a formula. What's our formula? It's n by n plus 1 by 2n plus 1 over 6. Where does that formula come from? Google. Google tells me that's the formula. And a little beyond the scope, that can be proved. But in this case, our n's cancel here, and n plus 1, 2n plus 1 over 6. So that's the expected value of the square. Not particularly interpretable formula. It's bigger, maybe. Smaller. Well, yeah, it's not particularly interpretable in terms of what it is. What we can hopefully interpret a little better is variance. And since we have now our first two moments, the first moment being the expected value, the second moment being the expected value squared, we can use our shortcut formula and we can get the variance. So variance and the shortcut formula says that the variance of x is the expected value of the square minus the square of the expected value. These two things are not the same, otherwise our variance would be 0. And in general, we can only push linear functions in and out of an expected value. You can't pull a square out without changing the value. But we have both of these at this point. The first one is n plus 1 by 2n plus 1 over 6. And the second one, we know the expected value is n plus 1 over 2, and we square the whole thing. And from there, it's some algebra. So I'm going to leave those steps to you. And if we do the algebra, we actually get a kind of nice little formula. It's n by plus 1 times n minus 1. So n plus 1 times n minus 1, and over 12. And the 12 denominator is at least believable in this case. That's a common factor of 6 and 4. And at least it's a simple formula. So that's the variance of discrete uniform. But as with most of these problems, if I want to get the variance, what I can do is I can get the first two moments, use my shortcut formula. That's almost always quicker than doing the definition. So our definition is that, of course, that variance of x is expected value of x minus its own expected value. That thing, that squared, close parens. And one could do that, but you're just going to end up finding expected value of x squared and x. So it's not really going to save you that much time. Okay, so we've done PMF, CDF, expected value squared, variance. What else can we talk about? What does the MGF of this thing look like? So let's talk about moment generating functions. So MGF, which stands for moment, moment generating function. And our moment generating function, by definition, is m of t. T is just a number. It's a real number. And m of t is defined as the expected value of e to the tx. So it's some function, e to the t, of a random variable. But that's not too scary, right? We have our law of the unconscious statistician, and the law of the unconscious statistician says I can calculate this. I just, instead of multiplying x times f of x, I multiply whatever the function is. In that case, it's e to the tx. So in this case, my expected value of e to the tx is the sum. X goes 1 to n, so that's over my support. E to the tx times the PMF, which of course, because we have the nice simple uniform, is just a 1 over n, and I'm going to bring that out front. All right, just 1 over n for all values x. And, okay, this is not the nicest formula, so let's see how how we can get this into a kind of simpler formula here. One thing we can do is, so let's just rewrite it. It's 1 over n sum x goes 1 to n. I can put some parentheses in. This is e to the t to the x. So just rewriting what I have, e to the tx. And what this starts to look like is it starts to look like a partial geometric series. And indeed, that's the way you can simplify this. So the partial geometric series says the sum of r to the I, where I goes 0 to n minus 1, is 1 minus r to the n over 1 minus r. Check your Calc 2 notes for that one. And so we just have to get it into the form. R in this case is basically going to be e to the t. Instead of I, we have x. And we just have to change our index a little bit. So, and we also have a 1 over n out front. So let's continue this on. We have our 1 over n. I can change x goes 0 to n minus 1. So that at least now kind of matches the indices we want for our formula. And it's e to the t. And now we have to, if I reduce my index by 1 in the kind of index set in the summation, I got to increase it in the formula, right? When x is 0, now we'll get 1. Before here, the first term was also e to the t to the 1. And it's still e to the t to the 0 plus 1 is 1. Okay. So I can play that game. And of course, I can take out one of my e to the t's. So I'm going to e to the t over n, sum x goes 0 to n minus 1, e to the t to the x. And by this formula here, with r as e to the t, we can rewrite this more simply. So we get e to the t out front. I get n in the denominator. And I get 1 minus e to the t to the n over 1 minus e to the t. And you could leave it there. If you want, you can do some other, you can multiply through by e to the t, and we get e to the t minus e to the t by n plus 1, using our rules of exponents, and an n and a 1 minus e to the t. So if you look up on, say, Wikipedia, this is what it could be something like this for the MGF formula, but it's all the same. And you could always say on an exam, you could always leave it there at that step. That would be good enough. Okay, and the only thing we have to make sure is that this formula here, r, absolute value of r better be less than 1. So this is true as long as e to the t is less than 1. So let's rewrite this and say for t such that e to the t is less than 1. And you can calculate that. That says, you can take a log of that, right? Okay. So that's the MGF for the discrete uniform. And we're kind of done with the discrete uniform at this point. So if we just do a real quick review of what was going on here. Discrete uniform distributed over some values 1 to n means equal likelihood at all these values. So that's kind of what the probability mass function looks like. CDF is the step function, stepping up 1 over n at each step, right? This is 1 over n, a step of 1 over n, a step of 1 over n, all the way up to 1. Expected value is kind of the balancing point, which is pretty easy to remember. It's n plus 1 over 2. And the variance has at least a cute little formula, n plus 1 times n minus 1 over 12. And then the moment generating function, which I don't expect you to memorize, but that's the form for the MGF. And that gives us a little practice with that. Okay, so that's the discrete uniform. The kind of mirror world, the continuous version is, of course, the continuous uniform distribution. And continuous uniform distribution is the continuous version of the uniform distribution. It actually, in many ways, the continuous versions are nicer. We don't have to work with all these summations. We don't have to remember any formulas for geometric series. And so our notation here is I'm going to say x, a random variable, distributed u, and I'm going to say it's over some arbitrary interval a, b. So this denotes that x is uniform. Let's say x is uniform over some interval a, b. And you can include the endpoints or not. We don't really care for continuous because the probability of being at the endpoint is 0. When we say this, this means that now we don't talk about probabilities of being at points for continuous distributions because the probability of being at any particular point you choose is going to be 0. But we can talk about the density at that point, and this means that there is a uniform density over whatever interval we have, a to b. And so if we want to look at, let's look at the, in this case is the PDF, the density function. And so here's our line, a, b, and we can look at the PDF, f of x. It's going to have some constant value over a to b and be 0 outside of that. So you could try kind of draw the function like this. This is our density function. And of course, we know that this value has to be constant, and we can actually figure out what that value has to be. We know that if I integrate my PDF over the support or the whole real line, I get 1. And in this case, this is the only thing in our support is AB. And so if I integrate f of x over AB, I better get 1. And if, let me erase that, if I know that f of s has to be constant, so I'm integrating some value c, some constant value c here, from a to b, and this just comes out to be c times b minus a, and that has to be equal to 1, so we know that c has to be equal to 1 over b minus a. So the value here I can write as, let's say c is 1 over b minus a. Another way of thinking about it is that the area under this curve has to be 1, right? I'd say the integral of my density over the support has to be 1. That's saying the area under the density curve has to be 1. Just the same way that the sum of the probabilities over the support has to be 1, the area under the density curve has to be 1. And so that area has to be 1. It has length a, b on one side. If that's 1, it has to have, or has length b minus a on one side. So it has to have a side length here, a height of b minus a. And that will give it to us. So that's the PDF. It's just 0 outside our interval and uniform density of 1 over b minus a in that interval. And we can look at the CDF, cumulative distribution function, and the CDF, capital F of x, is actually pretty easy in this case, is the integral from negative infinity to x of our PDF, which we now know is f of t. And this is because we have 0 density less than a, we can just say this is integral a to x, f of t dt, and that is, what does that give us? Let's think about this. So we know that f of t in this interval is 1 over b minus a. So this, we can replace f of t with this value, 1 over b minus a, just a constant. We can alternatively factor that out. And I just get the integral a to x dt, which of course is just, we keep my 1 over b minus a, and I get x minus a. Or I can write it like this, which is typically how to see it. X over a, or x minus a over b minus a. So that's what our CDF looks like, and has a cute little form. It's basically the percentage of the curve I've traced out if I'm at point X. So it's X minus A over B minus A. Notice when I get to B, I'll be at 1. So let's just draw a little picture here. Is my CDF? It's linear at X, right? This is just a linear function, mx plus b. The kind of linear function we're used to. It starts off at 0 if I'm below. So this is my CDF f of x. If I'm below A, my probability or my integral, my density less than that is 0. And then I kind of linearly increase from 0 up to 1, and then I flatline there. So this is the value 1 on my y-axis, and the slope of this thing is, let's think the slope of this thing is equal to 1 over b minus a. And that just comes from looking at this formula, right? Its slope is 1 over b minus a times x minus a over b minus a. So that intercept is that value. Cool. So that's the CDF. And you can think of it as if I have my PDF. What am I drawing here? Let's draw this right. A to B. I have my PDF, which is just a flat line, and it has a value of 1 over b minus a. If I'm at some value, little x in this interval, my integral of my PDF less than or equal to that value is just that area, that percentage of my total box here. So this is what's going to give me, and if you look, it has this side length is x minus a, and the height is b minus a. So you multiply those to get the area here, and that is exactly what we get in that formula. So that's the CDF, and that's actually a little bit nicer in the continuous case because it is just a little integral to solve. And I guess our case is that f, just to be complete. So our case is f of x is x minus a over b minus a if x is between a and b, and it's 0 if x is less than a, and 1 if x is greater than b. And you can say less than or equal to or greater than or equal to. Doesn't really matter. Continuous. We don't care. But there's little endpoints. Okay. So given our PDF, we can calculate the expected value for the continuous uniform now, and for the uniform distributions, we can basically guess at the value of the expected value, given the fact that, so here again is my PDF, 1 of b minus a, right? If I had a bar with uniform density, where would I balance? Where would I put my fulcrum to balance? Well, so I'm drawing my little fulcrum here. What's the balancing point here? I'm going to guess that it's the halfway point between a and b, which is their mean, a plus b over 2. That will give you that value right between. My guess is that the expected value is going to be a plus b over 2. So let's look at this. We can actually calculate it, right? So expected value, now for the continuous case, expected value of x is the integral of x f of x dx. And I only need to consider a to b because my density is 0 outside that. X and the density is uniformly b minus a and there. So that's my integral, a to b, x 1 over b minus a dx. And this is a really easy calc 1 problem. Pull that out. Integral a to b x dx. Right. That. And what do I get? I get x squared over 2, and I evaluate that from a to b. And that leaves me with b minus, a 2, a b minus a in the denominator, and then I get a b squared minus an a squared. And a little bit of math tells us that b squared minus a squared from high school is a plus b times a minus b, right? So this is a plus b, a minus b over 2 b minus a, and let's make sure this cancels out. It's I wrote this wrong. So be careful here. It's b minus a times b plus a. A plus b is the same thing. So this should really be b minus a, b plus a. Now I get the cancellation I want, and I'm just left with a plus b over 2. And that's the expected value, which is basically what we would have expected it to be. So that's nice. Expected value. And we can play the same game and get our expected value of the square of x. And the expected value of the square of x, of course, we're going to skip some steps. It's just x integral from a to b of x squared. And f of x dx. Integral a to b, x squared, b minus a, 1, dx. Pull out the b minus a, and I get, what, x cubed over 3 evaluated from a to b. And so this leaves me with b minus a, 3, and I get b cubed minus a cubed. And you have to remember the formula for the difference of cubes, or look it up at least. And the formula for the difference of cubes is that this can be factored as b minus a times b squared plus ba plus a squared. And we have still a 3 and a b minus a in the basement. And we get some cute cancellation here. So we get b squared plus ba plus a squared over 3. So that's the expected value of the cube. The expected value of the square. The reason we want that, obviously, is we want to calculate the variance. So we can calculate the variance from this thing, VAR, and using our shortcut formula, that's kind of wonky. Let's write it like this, x squared minus expected value of the square minus the square of the expected value. It's kind of a turn of phrase. So this is, again, shortcut formula to get the variance of this thing. So we just calculated the first part of this, b squared plus ba plus a squared over 3. And then we have the square of whatever our expected value was, which we said was just a plus b over 2. And some algebra will give us the answer, which gives us b minus a squared over 12. And that's just some algebra, so that's not too mysterious. 12 denominator, you can believe, common factor, common multiple, 3 and 2, or 3 and 4. And it looks, so some of these formulas look kind of the same from the discrete case to the continuous case. Not exactly the same, but there are some parallels. Okay. So we've done PDF, uniform, very, very simple. PDF, CDF is just a linear function. Expected value is a plus b over 2, and the variance is b minus a squared over 12. So the last thing, like we did in the discrete uniform case, is we can look at the moment generating function, mgf, and our definition, of course, m of t, where t is just some number, is expected value of e to the t x, and that is definition, by the law of the unconscious statistician, we can integrate e to the tx, f of x, dx. And simplifying this, we can ignore everything not in the interval a to b because our density f of x is 0. In the interval a to b, our density f of x is 1 over b minus a. We have e to the tx still, and we integrate with respect to dx. So let's do this Calc 2 problem, pull up 1 over b minus a, and what's my antiderivative of e to the tx? It's 1 over t, e to the tx, and I integrate this thing, or you can check that, right? Derivative of this thing with respect to x, you pull down t, cancels, right? And I evaluate this from x is a to x is b. So what do I get? I get b minus a. I guess I can pull out that 1 over, let's put that t in the basement there, because that's common. And then I get e to the bt minus e to the at. And that's the MGF. So there are different ways of writing it, but that's kind of how you see it. It's 1 over t times b minus a, e to the tb minus e to the ta. And this is valid as long as t is not equal to 0. If t is equal to 0, we're going to run into a problem here. Okay. So that's the continuous uniform distribution, and it kind of shares many of the properties of the discrete uniform distribution, kind of character of how we see the various forms. Nothing that you particularly need to memorize. I don't really expect you to memorize any of this stuff, but I expect you to be able to derive some of it. So if I gave you the PMF, can you give me the CDF? Can you give me expected value? Can you give me the variance? And can you give me the MGF? And none of this so far has been particularly tricky. There's maybe a little bit trickiness in the discrete uniform where we need to know the geometric sum, and we need to know the sum of some values, 1 to n, or the squares. Okay, so those are kind of very standard ways to start. Uniform, one of the simpler distributions. The next distribution we want to look at is also, in some ways, even simpler. It's called the Bernoulli, B-R-N-O-U-L-L-I, Bernoulli distribution. And this is the distribution of a coin flip. So we say x, B-E-R-N, and it has one parameter, p, which is the probability of success, is typically how we say this. This is the probability of success. And so, for example, if I flip a coin with probability p of heads, then let's say x is equal to 1 if heads, x is equal to 0 otherwise, then x has a Bernoulli p. So it's one yes or no binary experiment. Yes or no, flip coin, 0 or 1 is typically how it's encoded. And a probability p of getting a 1, probability 1 minus p getting a 0. But any kind of experiment with two outcomes, kind of nominally denoted 0 or 1, success or failure, yes or no, whatever kind of binary choice you have, two outcomes 0 or 1, and with probability p of getting a 1, then x, then this anything that follows this, the outcome either 0 or 1 follows a Bernoulli distribution. So this is very simple to draw the PMF So this is a discrete distribution. It's just 0, 1, two values, discrete. The PMF in this case, right, our support is 0 or 1. And the PMF is if the probability of getting, well, let's say this, the probability of getting a 1 is P, and the probability of getting a 0 correspondingly has to be 1 minus P. So this is my PMF, little f of x. And we can write this in symbols. A cute way of writing this is f of x, in this case, is, let's see, we can write it as p to the x times 1 minus p to the 1 minus x. And this is for x is equal to 0 or 1, and it's 0 else. Okay, what the hell is that? What's going on here is that x can take on the two values, 0 or 1, success or failure, yes or no. If x is 0, then I get p to the 0 goes away, that's just 1, 1 minus p to the 1. So I just get 1 minus p. If x is equal to 1, I get p to the 1, 1 minus p to the 1 minus 1 is 0. So the second part goes away, we just left to the p, and I'm going to take on 0 for any of the other values. So this is exactly what we had in the picture. A fancier way you'll see it written is this way. It's p to the x, 1 minus p to the 1 minus x, x is 0 or 1. And that's just kind of binary way of encoding things. So that's the PMF. Two point masses, 0 or 1, yes or no. Probability p of getting 1. And by p, of course, has to be, go back up here and just be real specific here. This p, this parameter, p better be 0 in the interval 0 to 1. I suppose it could include the end interval, so 0 to 1 inclusive. That's very boring if it's 0 or 1, though. Okay. PMF, great. We can, of course, look at the CDF, right? So what's the CDF of this thing? Of course, we're just going to sum, all right? So let's just draw a little figure here. Here's our support value, 0 and 1, and we're just going to sum all the values less than or equal to. And so certainly if we're less than 0, let's say f of x, there'll be a couple cases. If x is less than 0, we have no mass for summing up, so we're 0. So we'll go 0 all the way up to 0. At 0, it jumps up. We include this mass 1 minus p. So we jump up. We jump up here to 1 minus p. And so if x bigger than equal to 0 but less than 1, so we're anywhere from here all the way in between these, we're just going to continue on, step function over until we hit 1, and at 1 we jump up to 1, actually. Right? At 1 we add in last mass, so we have massive 1 minus p, anywhere between 0 and 1, and then as soon as we hit 1, we jump up, we add on this last bit, that brings us 1 minus p plus p, gives us 1. So we get 1 minus p in here, and we get a 1 if x is bigger than or equal to 1, and that just continues on this way. So that's the CDF. Again, a pretty simple CDF for Bernoulli. And this is one of the nicer random variables because everything is going to be real quick to derive here. So what else can we look at? We could look at expected value, expectation. Expected value of a Bernoulli random variable is, all this notation is a little bit ridiculous. Our support is 0 to 1, so you can write it like that. Sum from 0 to 1. It's x times f of x, which is just, of course, when x is 0, it's 0 times f of 0 plus 1 times f of 1. 0 times whatever is 0. So we just get f of 1 here left over. And f of 1, of course, if we go back up to our PMF, f of 1 is just p. So if I tell you I have a 50-50 chance of, if my p is equal to 0.5, let's say I flip a coin. If the event that it comes up heads, let's say it's 1 if it comes up heads, it's 0 if it comes up tails. What's my expected value? Well, it's 0.5. I'll get 0.5 heads on one flip, right? So expected values don't have to fall into support. You can never, of course, get 0.5 flip, heads with one flip. But kind of expected value, if I look at the balancing point of this distribution, it's going to fall somewhere between 0 and 1. If p has a higher value, it's going to be somewhat more weighted over towards p. And if 1 minus p is larger, it's going to be over more towards 1 minus p. And if they're equal, it'll be exactly between them. So for 0.5, it'd be exactly at 0.5. If p is 0.75, it'll be 0.75. So the expected value of Bernoulli is just the parameter p. So that's nice and simple. And equally simple to get is we can look at the expected value of the square, right? And I'm going to skip all the formalization here. It's now 0 squared times f of 0 plus 1 squared times f of 1. Of course, that is just going to give me f of 1 again, which is p. Indeed, as an aside here, every moment of this thing is going to give me p. If I look at the expected value of x to the r, I'm just going to get, you can play that same game, 0 plus 1 to the r times f of 1 is p. So every single moment of this thing is p. So that tells you something about what the MGF is going to look like when we derive that. So it's the expected value is p, expected value of the square is p. And so this makes getting our variance pretty straightforward. If I look at the variance of x, this is, of course, shortcut formula, expected value squared minus expected value of the squared minus the square of the expected value. It's p minus p squared, which is p by 1 minus p. Okay, so that's the variance, which looks a lot like the variance for a binomial. If you go back to our example of binomial, and indeed the binomial is, this is a special case of the binomial. So yeah, if n is equal to 1, this is, you're going to get it Bernoulli. So note, Bernoulli p is the same as a binomial distribution, np, where n is equal to 1, right? Binomial experiments, I do n experiments, I look at the sum of the successes. Bernoulli, if I do one experiment, I look at, is that success, right? So it's just a binomial case with n is equal to 1. And you can see that from expected value, from the square of the expected value, or from the expected value of the square, variance. Go back and look at a binomial case. These are all the cases if I just plug in n is equal to 1. So nice and simple. And the last thing we want to look at here for our binomial, or Bernoulli random variables MGF, m of t is the expected value of e to the tx. That's our definition. And we can, of course, write this out, kind of cumbersome. It's the sum over 0 or 1. Those are only the values in our support. E to the tx, f of x. And we can really simply write this out. It's e to the t times 0, f of 0, plus e to the t times 1, f of 1. Plugging in 0, 1. E to the t 0 is 1, so e f of 0, plus e to the t f of 1. F of 0 is 1 minus p, f of 1 is p. So we'll get 1 minus p plus p e to the t, which again, if you remember our MGF for a binomial, which I believe we derived already, that this is exactly what we get when n is equal to 1. But that's the MGF there. Okay. So those are the real nice and simple distributions. So we look at uniform, discrete, and continuous. We look at Bernoulli, which is a special case of binomial, when I just have 0 or 1 outcome. And the next one we're going to look at, we looked at a little bit before, but let's let's just finish off all the properties. And that is our world famous normal distribution. Normal distribution, or Gaussian distribution. And it has the famous bell curve shape. It has a mean we derived of mu, and it has a variance that determines the width of this peak. That's sigma squared. So we write x distributed, normal, mu, sigma squared, and those are the mean and the variance. So we showed previously, so we showed a couple things previously. First of all, our PDF looks like this. So it's f of x is root 1 over root 2 pi sigma squared exponential negative 1/2 x minus mu squared. And we also showed, so let's say we showed that the expected value of this thing was mu, surprise, surprise, and that the variance of this thing is sigma squared. And those are our two parameters here. Mu can be any number, and sigma squared has to be some positive number. That's variance has to be. And this PDF is good for any x and r. And this is the shape it gives. It's a negative exponential. It's centered at mu. Okay, so those are properties we saw in previous notes. I believe. Let's think. Did we show? Well, we showed. Well, maybe we didn't show this one. So let's actually go back and let's talk about how to get these two. So what did we actually show? We showed. We showed that. Let's write it like this. We showed that the integral of this thing is actually 1, right? Or we showed it for a simple case that it's 1, and we now actually should be able to show that the mean and the variance are indeed as we think they are, mu and sigma squared. So let's look at how to do this. So let's look at the first one, because of course we're going to use our shortcut formula to get variance. I'm going to skip the CDF. So the CDF has no closed form. There's actually not an analytical way to write this thing down. You can only solve it through numeric integration. You can't just write down a simple formula. So the integral of this, which makes it amazing that we can show the whole integral is 1, when actually the integral of, or just part of it, doesn't really have a closed form. CDF has no closed form. If we want to look at expected value, expected value. So let's look at how to do this. How do we calculate the expected value of this thing? So we believe that, right, as I wrote above, that the expected value of the norma should be mu. So we have the formula, right? Expected value of x is the integral x f of x dx. It's the integral over all values, because the support in this case is actually all possible values. And this thing is the integral of, well, we have our formula. It's x. And in the basement, we have 1 over root 2 pi sigma squared, exponential, negative 1/2, x minus mu squared, dx. And we can make a change of variables here, just to simplify our lives. And the change of variables is we're going to introduce a new variable y, which we're just going to say is x minus mu. So we're going to kind of recenter things. Or x is equivalently y plus mu, which just means dy is dx, right? That doesn't change. That's pretty nice. If we make this change of variables, we can pull out a constant, 1 over root 2 pi sigma squared, and we get the integral of x is now y plus mu. replace that x, and we get exponential -1/2. X minus mu is just y, so actually this just becomes y squared, and dx becomes dy. And we're still going to carry around this constant, 2 pi sigma squared. But I can break up this integral by distributing my integral across my summation. So we're going to get one integral is y dxb -1/2 y squared dy. And we're going to get a second integral, which I have my constant out front. And I'm going to get the integral of mu times this thing. What are we missing? We're missing a sigma squared here. No one's going to call me on that. Haha. I'm missing a sigma squared. Let's not forget our little sigma squared friend here. So sigma squared, and sigma squared. Okay, and the sigma squared here. Okay, so that seems right. Now, this integral, so we have two integrals we want to solve. We can solve this one with integration by parts. And what we're going to do, actually, this is going to be even easier than integration by parts. So let's actually look at this function. If we look at the function here, let's call this thing g of y. G of y is a, we call this a odd function. Odd function meaning that if we look at g of negative y is equal to negative g of y, right? If I plug in g of negative y, I'm just going to get a negative out front. And so we get this kind of odd function. And we know that if I integrate an odd function, over a symmetric interval, right? So an odd function, of course, looks something like this. This, right? This is kind of a pretty typical odd function where it has this kind of symmetry over the axis here. If I integrate an odd function, the areas cancel. So this area here is going to be the same area as there, and so I get a minus a as my integral is 0. So if I integrate some kind of odd function like this over a symmetric interval, say negative b to b, I'm going to get 0. And so I'm integrating this thing over negative infinity to infinity. I'm integrating an odd function, which is a symmetric interval. And so my first integral is 0. So actually that first term turns out to be a big goose egg. Nothing. The second integral here, very nicely, is we could just pull out, so that's the kind of first integral. The second integral is mu times the integral of root 2 pi sigma squared. I get a 1. I get exp -1 over 2 sigma squared y squared dy. And we just have to recognize this as the PDF of a normal 0 sigma squared, right? So that is the PDF. If you go look at our definition of what a normal distribution looks like, if mu is 0 and our variance is sigma squared, this is the PDF of a normal 0 sigma squared. Of course, we're integrating over the whole line, and so the integral is unity. The integral is 1, and so we're just going to be left with a mu out front. So mu times 1. So we go back down to our answer here. It's 0 plus mu, which is mu. Right? And this, of course, we were deriving. If you have to remember what we're deriving here, we're deriving the expected value of x. So that, a little trickery there. We need to know how to integrate an odd function over. We need to be able to split this. We say integrate an odd function over this interval, over this kind of symmetric interval of 0. And we recognize that the second part here is just the integral of a normal 0 sigma squared instead of a mu sigma squared. And so that change of variables here did that trick for us. But all we're left with at the end of the day, we're calculating the expected value of x, which we knew, or we expected to be, as it were, mu. And indeed, that's what we get. We get mu at the end of the day. So that's the mean. And we can play a similar-ish game for the variance. So let's real quick look at the variance here. These are proofs that I would not expect you to recapitulate on the exam, but it's good to kind of see the mechanics of how this works. Okay, so variance of a normal random variable. And the variance of this thing, we have a formula, right? So the formula here, the shortcut formula typically is the way we calculate variance, but we can go back to the definition. And in this case, we use mu for expected value, and it is also, not coincidentally, the name of the parameter. So this is exactly the variance of a normal random variable. So that's the formula. And we can actually just calculate this integral, right? So it's a function. It's effectively a function of my random variable. The function is x minus mu squared. So we can calculate this expected value by integrating x minus mu squared by f of x dx. Okay. And when we do that, we can plug in our formula for what the expected value, or sorry, what the PDF of a normal random variable is. So this is the integral r x minus mu squared, and our PDF has this form, 1 over 2 pi sigma squared, exponential -1/2, -1 over 2 sigma squared, x minus mu squared dx. Okay. And again, we're going to use a tricky change of variables. We're basically going to do z-score. So we're going to define y as x minus mu over sigma. So sigma being the square root of sigma squared. If I do this, then dy is 1 over sigma dx. And my integral above here can now be rewritten. I have my root 2 pi sigma squared that stays out front. X minus mu squared is almost y squared, but I actually have to add an extra sigma squared. So this is sigma squared y squared. And I still get exp, but now I just get -1/2 y squared. And I get a dy times sigma. So I need to throw another sigma out front here. Because dy, or this is equivalent to saying I want to replace my dx, is sigma dy. So sigma, throw that up front, dy. Instead of x minus mu squared, I get sigma squared y squared. And the exponent now is actually very simplified. It's just -1/2 y squared. Okay. So we have a lot of stuff that we can factor out at this point. Let's see. What do we factor out? Well, sigma over square root of sigma squared is, those both cancel. I get a 2 pi in my basement here, root 2 pi in my basement, and I get a sigma squared I pull out. And then I'm left with integral y squared exponential negative 1/2 y squared dy. Now I'm not going to solve this integral totally. I'm just going to say that we can do integration by parts. So here's our integration by parts problem. And I'll give you, and you can work out at home, how to do this. U is going to be y, and dv is going to be y exp to the negative 1/2 y squared dy, right? So this thing is now just sigma squared 2 pi integral of u dv. And when we solve this integral, the integral over all possible real values, turns out that, I'm going to say can show, that the integral, if we write this out, so integral of u dv is going to give us root 2 pi. And I'll let you think about how that can be done. The hint is you're going to have to recognize part of that integral as the PDF of a normal random variable. That's where you get this 2 pi from. And so altogether, whoops, oh no, come back. Pulling this out, if we pull this out, we get sigma squared root 2 pi times root 2 pi, which cancels and just gives us sigma squared. And of course, at the end of the day, what we're calculating is variance of x. And so indeed, as we thought, the variance of x is sigma squared. And that just involves solving this integration by parts problem, but that's not something I need to do in lecture. And you can think about how to do that. Okay, so that's almost everything for the normal. The only last thing we haven't really talked about, so we've done expected value for normal. We did PDF, which we've given you. So that's just the definition. That's, you know, kind of the bell-shaped PDF here. That is the mathematical formula for it, this thing involving it. You know, this exponential, negative 1/2, blah, blah, blah. That's the formula for the PDF. There is no closed form formula for the CDF, unfortunately, but we can show what we set out to show here. Expected value is mu, variance is sigma squared. And so the last thing we should really derive is the MGF. So let's get the MGF for this thing. Okay. So MGF. And so basically, you know, what we've been doing this lecture is a bunch of practice on MGFs, CDFs, PDFs, BMFs, expected values, expected functions, expected values. And the MGF is not too bad for a normal. So the MGF of a normal, of course, our definition, M of t, is expected value, e to the tx, and this is true for any random variable x. And we have our formula. We can expand this with the law of the unconscious statistician. This is the integral over r e to the tx f of x dx. And we have a formula for this kind of somewhat nasty formula for the normal PDF. And that looks like this. Don't forget your sigma squared. Okay. And we're integrating with respect to x. So how do we solve this one? Well, we can absorb, we have two exponents here. We can actually combine these together. So what I'm going to do is I'm going to rewrite this thing. First of all, we should note that x minus mu squared is, of course, x squared minus 2x mu plus mu squared. And so we can rewrite this integral. We still have our constant, 2 pi sigma squared. That gets toted around. And we can write this all as one bit exponent now. And I'm going to write this as 1/2 sigma squared. This is x squared minus 2x mu plus mu squared. And then I want to bring in my tx, and so I can bring in tx, but I gotta multiply it by the proper value here, proper constant out front here. And so if I'm going to bring that thing in here, let's see, tx, I need to multiply by a 2 and by a sigma squared, right? And then we integrate this with respect to dx. So I'm allowed to, so right, this 2 and the sigma squared will cancel with that. And I'm allowed to bring that in. So what, although presumably this should be a negative, right? I need a negative. Okay. Now that should be right. Okay. So what am I left with? I want to convert this into the PDF of a normal. It's really what I want. I would really want to recognize this as the PDF of a normal. And so what I'm going to do is I'm going to complete the square. Okay. So what do I have? I have an x squared. I have a mu squared. So x squared, mu squared. And then I have a minus 2 and an x I can factor out. And what I'm left over with is a mu and a sigma squared and a t. Sigma squared t, right? Okay. So that's what my square is, just rewritten out. And I'm going to try and complete the square. Try to write this in a nice way. And we can show, through a little completing the square exercise, that what I really want to do is I want to write this as x minus mu plus sigma squared t, right? I'd like to say it's that, but it's not quite, because that's not quite what it is. I can do that. Of course, I need to keep on my mu squared here, but I have to account for this term mu plus sigma squared t that actually doesn't show up. Okay, so now when I expand this out, so these two things, this is just kind of a, I mean, think about how you want. I think about it as completing the square. How these things kind of show up is now if I compare these are the same. My mu squared is still there. If I square this thing out, I get x squared. I get a minus 2x times this thing, mu plus sigma squared t. Then I should get a plus, oops, let's not, mess this up too much. Is that supposed to be a plus sign there? Let's think about that. Yeah, I think that should be right. Then we get a plus, plus minus, right? So it would be x squared minus 2x mu plus sigma squared t plus 2, plus mu squared, mu plus sigma squared t. And so I subtract that off. Now they're going to be equivalent. Point being, whatever algebra, you can get this squared. You can get this term up here. You can write it like this. And so this means I can expand out my integral here. I get, so let's see, what do I get? I get the integral over r 2 pi sigma squared, just like that, and exp. And I can break this thing up, so let me break this thing up. Let's see, so I'm going to say it's mu squared plus minus mu squared minus mu plus sigma squared t squared. It's negative 2 sigma squared, right? And what I am left with here, then I can multiply exponentials, that's the same as adding them. I'm left with my square here. So this is negative 1 over 2 sigma squared x minus mu plus sigma squared t x minus mu plus sigma squared t squared, right? Okay. That's my integral. And if I notice a couple things, so this whole integral is with respect to dx, right? If I just look at this term and this term, these combined are the PDF of a normal. Now let's get this right. It's a mu plus sigma squared t is the mean, and the variance here is sigma squared. So if you look at the PDF of a normal, where the mean parameter is mu plus sigma squared t and the variance is sigma squared, this is exactly would be the combination of these two terms to give that PDF. So actually, if I were to integrate those, that would give me 1. And indeed, I can factor out this term. So let's just say factor this out. Bring out. And what am I left with here? So we'll get exp. Okay, what am I left with? Negative 1/2 sigma squared mu squared minus mu plus sigma squared t squared, close paren, and then the integral of, basically I'm going to write it this way, of a normal mu plus sigma squared t sigma squared. And so this whole thing gives me 1, goes away. And so this is going to be what's all that's left over. So this is going to be my MGF, which can be simplified. I'm just going to say simplify to just have to expand things out and cancel some things out. What you'll get at the end of the day is actually quite simple. Is this. So this is the formula typically see if you look it up on, say, a Wikipedia page. It will be exp of mu t plus sigma squared t squared over 2. Okay, that was a lot. So let's just walk back through the steps real quick of what was going on there. I wanted the MGF. MGF is m of t is effectively e to the tx, right? That's my formula. That's what happens if I plug things in. I'm just going to combine this e to the tx with the exponent already in the PDF. And then I have to combine this. I'm going to do some really clever algebra. And we're going to rewrite that exponent cleverly so I get this term here that factors out. This thing factors out. And the rest of it is just the PDF of a normal mu plus sigma squared t sigma squared. That thing will integrate to 1. I'll just be left with this term that's left over, and some algebra will simplify it to this. So this is, I wouldn't expect you really to rederive this on an exam, but this will give you the MGF. We can test this, so God only knows if this is correct, right? We can test this because we know that if I look at dm dt and I evaluate it at t is 0, that should give me my expected value, right? That should be expected value of x, which we know for a normal is just mu, the parameter, the mean parameter. And dm dt is derivative of this thing with respect to t. So we, by chain rule, this gives us, we have mu plus sigma squared t. That's the derivative of the exponent times exp of mu t plus sigma squared t squared over 2. And so dm dt, evaluate that t is 0. This whole thing goes to 1. This thing goes to 0. All that's left over in that is mu. Okay. So that's the MGF of normal. So the normal can be, as you've seen several times, it can be a little cumbersome to work with. but it gives you kind of what you would expect there in terms of mean and variance. It's a little bit tricky to show, but the mean is mu and the variance is sigma squared. Okay, so there's a really useful theorem that I think is worth mentioning at this point. And the really useful theorem here is what happens if we look at linear functions of a normal random variable. So let's say linear functions of a normal mu sigma squared random variable. So if x has a normal mu sigma squared distribution, then if we define a new random variable, let's call it y. Let's write this legibly here. Y, and y is some constant a times x plus b, then here's the nice thing. Y also has a normal distribution. That's not generally true. If I take a linear combination of a random variable, or a linear function of a random variable, it may not be in that same family. A linear function of a Bernoulli is not a Bernoulli. But for normals, they're always going to be normal. Linear function of normals is normal. And its normal, and its mean is a mu plus b, and its variance is b squared sigma squared. So it's normal, and we can really kind of quite straightforwardly calculate what the mean and the variance parameters are. So the intuition here, for why this is true, is that if we look at the expected value of y, this is the expected value of ax plus b, is we know that expected value is linear, and so we can distribute the expected value through. We just a mu plus b, which is indeed the mean for a new random variable. Okay, so that makes sense. And if we were to look at the variance of y, and we would get that this is the variance of ax plus b, and our theorem for variances says that this is, we can ignore the additive constant b, and all we have to do is pull out the a and square it. Is a squared times the variance of x, which is a squared sigma squared. And, whoops, oh boy, so my theorem's wrong here. It should be a squared sigma squared. Okay, right, so good thing I proved that. That shows that kind of very straightforwardly that you just scale up by the linear scaling factor. So that's the intuition. That's not actually a proof. And if you're wondering why do I even need to know the MGF of a normal? Why do I have to go through this whole derivation? Proving something like this is exceedingly easy if I know the MGF. So the MGF of a random variable y, we said this kind of characterizes the random variable. We know that that y is ax plus b, and we had this theorem that the moment generating function of a linear function, we can say it's just what can we say? We can say that it is e to the t b m x of a t. Right? That's our theorem. So in this case, we know x is normal, and so we know what the form of the moment generating function is. It's mu t, so instead of t we have at, plus sigma squared over 2 times t squared, or a squared t squared. All right? If we go back up to our form of our MGF up here for the normal, we're plugging in for t, we're plugging in at. Okay. And we can always bring our TB in here. We can bring this in. This is a mu plus b times t plus sigma a squared sigma squared times t squared over 2. And we can recognize this. This is the MGF of a normal, a mu plus b, a squared sigma squared. Right? If I were to write out the MGF of that normal distribution, it would exactly take that form. And so we know that the MGF of y is the MGF of that kind of normal random variable, and so that has to be the distribution of y, because the MGF tells us everything we need to know about it. Okay, so I'm going to stop there. That's enough for today. So that we went through today, we went through the discrete uniform, the continuous uniform, and we talked about the Bernoulli, which is very simple, discrete, and we talked about the normal.